Okay, hello everyone. I'm Henry, and I'm trying to talk about the method of undetermined coefficient 2. Um, I want to do a PowerPoint of it, but I discovered that there are many handwriting parts, so I try to record the presentation by the handwriting sheet like this. All right, so first let's consider a kind of equation like this. Um, so in this equation, we can see there's a little bit more information for us, right? So first, let's look at it step by step. For A, B, and C, they are constant, and for lambda and the omega, they are real number. And for P and Q, they are polynomials like, I think all you guys know polynomials, like x squared plus 3x plus 1, something like this kind of things. Polynomials. They are polynomials. And then let's consider another specific section. So we let lambda equals to 0. Then we know this equation, this part will become 1, right? So there's only the right part of this equation. Then the equation will become this. Right. So the goal is to find a particular solution to this equation. Our goal is to find the yp of this equation. Okay, so the yp is the goal. We're going to find the goal of this. All right, so in order to find the yp, we assume the yp equals to ax cosine omega x plus bx sine omega x. All right, so we assume that. So why we try to assume like this, there's a reason. There's a reason we can assume yp like in this form, and both A and B, they are also polynomial of x. So if you are trying to differentiate terms like xr cosine omega x or sine, so we can get what we can get is like negative omega x power of r sine omega x plus r x r minus 1 cosine omega x. All right, so as we can see, the sine plus cosine, this kind of structure will not be changed, but the only thing change is the exponent, right? So that's why if we have a kind of structure of cosine and sine, we are trying to find the particular solution, we can assume yp is also the same kind of solution, the same structure of the solution, and with a and b two polynomial as before cosine and sine, right? Okay, so then we already assume yp in this kind of structure. We'll find a new equation about ax and bx. We'll find so which is a yp's second derivation plus b yp's first derivation and plus c yp equals to the there's another polynomial. We can set another polynomial as fx cosine omega x plus gx sine omega x, right? Right, because we're trying to find the initial equation of this. So we assume the particular equation is that. So for this equation, there will be a new equation like this. And then if fx and gx equal to px and qx, so that means if we find a and b is able to let f equal to p and g equal to q, so that means our answer is right. So we can get the right yp, right? And so this will make a systematic way to find ax and bx, which together form the particular solution yp. So yeah, this technique works well when the right-hand sides like this include polynomials, sine and cosine, or a combination of them, right? So that's why that's what we are going to do. So that's what the method of the undetermined coefficient 2 is trying to talk about. And okay. All right, so if we try to, and let's talk about a theorem. So now we know about this structure. A, Y. I just want to write it again, so we don't need to go back. Okay, so both P and Q, they are polynomials. And okay, at this time, omega bigger than 0. And A, B, and C, they're constants. Okay, now we are trying to solve AX and BX. Now we are trying to solve AX and BX. So this theorem tells us if A and B and C, they are constant, and P and Q are polynomials, and omega bigger than 0, and it's a positive constant, should be a positive constant. Then we can say ax and we can say ax equal to a0 plus a1x plus a2x squared plus unto ak xk. Okay, and bx equals to b0 plus b1x plus b2x square xk. And the k is at the largest degree of the polynomial of p and q. Okay, where k is the largest degree of p and q. Okay. And also at the same time, there's some we need to there's some requirement of, if we can write this immediately, there's some requirement. So first, cosine omega x and sine omega x, they should not be the solution of the complementary equation. They are not solution of the complementary equation. All right. So yeah, because I don't need to write a one here. So if they are a solution of the complementary equation, so we need to add extra x in A and B. So let's talk about this later, but right now we just know there's a requirement here. Okay. All right. So if so there's a specific equation, a specific section, special section. So if cosine and sine, they are the solution of the complementary equation. So ax we should add one more x after that. Yeah. And bx should be the same. Yeah. So in this case, we need to make sure the structure of the solution should not be should be the should not have conflict with the solution with the complementary equation. So okay, so for let's do a small summary of this part. So this series 5.5.1 talk about if the right part like px cosine polynomial of p if there are two polynomial between if the right part include polynomials, cosine, and sine, and or a combination of them, we can use ax. We can if we put it if we plug in into the equation, we can solve ax and bx in the polynomial of a and polynomial of b. So then we can get the particular solution of this equation. All right. Let's talk about an example to be more to let us more understand this theorem. So, for example, there's a there's an equation look like this. All right. Let's see the right part of this equation. We have a 5 cosine 2x and 10 sine 2x, right? So we can see, oh, the 5 and 10, they are two constants. So we know the biggest the biggest k is the largest degree of p and q. So the k here equals to 0, and there's a cosine 2x and sine 2x on the right side, so we can assume yp equals to a cosine 2x plus b sine 2x directly, right? Then we do the derivation of yp and the second derivation. Okay, we need to solve these two in order to get, because we have the second derivation on the left side and the first derivation on the left side, so we try to get so yeah, we can also include a and b in order to solve a and b. After that, should be negative 2a sine 2x plus 2b sine cosine 2x. So the second derivation, do the same thing. It's just a derivation of the first derivation. $2x, right? All right, and we plug in these two into the left side. So what we can get is negative 4 minus negative 2. Negative 4. We should put the cosine together, right? Sine and cosine together. And there's a 2. So negative 4 minus okay, I just copied m plus a cosine 2x plus b sine 2x. And what we can get is equals to 5 cosine 2x plus 10 sine 2x, right? And we put all the cosine and sine together, we'll get negative 4 plus 4, wait, not plus 4, so it should be, so for the cosine, negative 4 minus negative 4, so plus 4 should be negative 3, right? Oh, no, sorry. So negative 4 plus 4b, negative 4a plus 4b plus a, all right. So it should be negative 3a cosine 2x. Oh, we can add them together. Negative 3a minus 4b cosine 2x plus 4a minus 3b cosine, should be sine 2x equals to this part, right? So we know this part is 5, this part is 10, and we can get a and b. How to get a, b? A equals negative 6, something. A equals to a equals to 1, b equals to negative 2, right? Let me check again. 1, yeah, equal to 1, b equals negative 2. So we can have a yp immediately equals to cosine 2x minus 2 sine 2x. Okay. Now this is the particular solution of this. Okay, so let's find another paper. Talk about another problem. Okay, so we talk about the normal problem. So now let's talk about a special problem. So in the special section, if so the cosine and sine are solution of the complementary equation. So now we will see what will happen. So another example. For y equals to 8 cosine 2x plus 12 sine 2x. All right, so we know that cosine 2x and sine 2x is the solution of y have it's the solution of this. Cosine 2x and sine 2x. Our solution of y, the second derivation of y plus 4y. When this thing happened, we cannot use the simple form yp equals to a cosine 2x plus b sine 2x. We cannot use that. We need to add another x before that. So we assume yp equals to x a cosine 2x plus b sine 2x. Yeah. So if we try to do that, we'll do it again, and we do the derivation again, but this time make sure we need to add more things here. 2x plus sine 2x plus x negative 2 a sine 2x plus 2b cosine 2x. And the second derivation would be this one will be a little bit more longer, but I already do it before, so I can tell you something like this. Yeah, it's really long. All right, and we plug these two back to the equation. Then we will get, what we get is negative 4a plus 4b sine 2x plus 4a minus 4b sine 2x equals to 8 cosine 2x plus 12 sine 2x. Now we get this one is 8, this one is 12, right? So a equals to negative 3, b equals to 2. All right, now the yp will be x negative 3 cosine 2x plus 2 sine 2x. So yeah, that's the yp of this. All right, so these are the two kind of problem we're able to solve by the theorem 5.5.1. Okay, now so all these problems, they are the polynomial part, they are constant, so it means k equal to 0. So now let's have another equation for the polynomial. Like we need to use the k right now. Okay, we need to use the k right now. let's have another example. So we find out that the px and qx's, one is the polynomial with x, another one is the constant 10. So now we are going to, what we are going to do is, so we know now the k equals to 1 because k is the larger degree. So so we can so assume that assume yp equals to ax plus a1x cosine x plus b0 plus b1x sine x. So if we see a polynomial with a higher k, we ignore the lower one. We do the a0. We let the ax and bx in this way. Okay. And we do the same things. We do the first derivation of it, and we do the second derivation of it, and we plug in back to solve a and b. Okay, to solve a and b, and just so according to the time, I will just give the solution of it. Okay, so for the first one, we can get a1x plus a0 minus b1x minus b0 sine x plus 1 plus b1x plus b0 cosine x. Second one is negative 2. a1x plus a0 negative cosine x minus 2, put minus here, minus 2 a1 plus b1x plus b0 sine x. Okay, when we put it back, we can get yp plus 3yp first derivation plus 2yp. Now we can get such a very large thing. It will be a0 plus 3a1 plus 3b0 plus b1x plus a1 plus 3b1 x cosine x plus b0 plus 3b1 minus 3a0 minus a1 plus negative a1 x sine x. All right, so we let this part equals to 16 plus 20x, and this part, so this part equals to 16, this part equals to 20, this part equals to 10, right? And we know that yeah, this one equals to 10. So we can, what we can get is a plus 3b1, a1 plus 3b1 wait, there's something too much information here. We can get an equation. We get many equations here. According to the time, I just put everything here. Yeah, so the things we have to know is like we can actually solve a0, a1, b0, and b1 from these two equations, and we can also separate those equations into these four equations. Okay, so after we solve that, we can get a1 equals to 2, b1 equals to 6, a0 equals to 1, b0 equals to -1. So now we put these things back to our assumed particular solution. It will be 1 plus 2x cosine x minus 1 minus 6x sine x, right? So that's how we use 5.5.1 to solve it. Okay, so now let's talk about the second theorem. So it's in a book which called 5.5.4 theorem. So if the assumed yp equals to ax cosine omega x plus bx sine omega x, then and a and b, they are polynomial, then yeah, you can actually derive the corresponding polynomial for yp. Yp's first derivation and yp's second derivation, and the other expressions other expressions by systematically replacing coefficients in a and b. This will let you directly switch. So the coefficient. Wait. So the coefficient of the of sine. Let me think how to say it. Yeah. So the coefficient of sine omega x can be solved by only a switch change cosine omega x to find can be found. It doesn't matter. So it'd be like b0 b1 something bk equals to negative a 1. Yeah, this way is better to explain. Negative a k to get. Okay. All right, let's still use one example to talk about this theorem. For example, sorry, according to my English, it's better to use this way to explain. Yeah, okay. Assume the equation is like this. All right. We can see with the same way the biggest k should be 1, right? And we assume yp equals to for this one we need to we assume a0 plus a1x cosine x plus b0 plus b1x sine x, right? Oh, and also because we see that a8 minus 4x and 8 plus ax is the it's a special case, right? And cosine x and sine x, they are solution of second derivation of y plus y, so we need to add x here on both, right? So we do the first derivation. It will be a0 plus a1x plus 2a1x plus b0 x here cosine x plus b0 minus a0 plus b1x plus 2b1x sine x. And for the second derivation, too much, but I will, according to the time, but when you put it back to the but we don't really need that, right? We don't really need this. So we yeah, we don't really need it, doesn't, because we doesn't means we don't need to put that. So I will just show the solution. So the yp all right. So I just show the solution. Okay, so you all know how to do it, but I just want to show the how this theorem do. Okay. we let so the a1 become 2 and a0 is -1, b1 is 3, b0 is 2, and we put these things back. So yp we can get is x cosine x plus 2 minus x sine x. And then we can discover that we can discover that theorem 5.5.4 works, right? Let's talk about the next part. Sorry, I have a message to answer very quick. Okay, I'm back. Okay, I'm back to talk about the next example. So this example will be a little bit more difficult, but I will show you how to do it. So if we try to solve this problem, we discover there's an e -2, right? So we need to solve this because we don't want to see that, right? So in order to solve this, we can do this way. We let y equals to ux e -2x, right? So, and the y derivation would be derivation of u e -2 x -2 u. This is 2. 2u e x. We need to find the first derivation and the second derivation, and then we put it back. So this will be so now okay, so now if we divide this part on both sides, we can have a new thing. We have a new equation. And we would use the same way to solve the particular solution of this equation, because now we can use the theorem. Now we can use theorem 5.5.1. All right. Then we can get the solution. That's how to solve this kind of thing. Yeah. So so this part is more important. Let me see if there's any other parts. Okay, so since I check on the textbook, I think there's no part. So that's the end of today's presentation. Okay, thank you very much for listening. I know there's some emergencies during the presentation, but yeah, that's all for today. Okay, thank you.